bit nervous, but if you haven't met me before, I will just give like a brief introduction of myself and what I did in the last few years in physics. So I'm Italian. I come from a little town, Bergamo, which is very close to Milan in the northern part of Italy. And you can see here some highlights of this city, which has like an upper part. It's called Città Alta, so the upper town. And the walls that surround the upper town, the Venetian walls, are actually UNESCO World Heritage. So I suggest you to visit it if you are in the area. There is also a convenient Ryanair-dominated airport. And then for the university, I moved from Bergamo to Trento, which is very close to the Alps. It's famous for tourists for the Dolomites. It's 2 hours away. This is like the main square in Trento. I stayed there for my bachelor and my master, and that's actually when I got into nuclear physics, and I got passionate about the structure of nuclei and nuclear reactions. And then from Trento, I moved 9 hours north in Mainz, close to Frankfurt, where I did my PhD. Here is an aerial view of Mainz with the dome and the Rhine that crosses it. This is very nice. And then after my PhD, which I concluded like in July last year, I moved to the States, so this was like a bigger jump. And from Germany, I actually got to the US, and my position is a fellowship which is shared between 2 institutions. So the Facility for Rare Isotope Beams at Michigan State University, which is a big accelerator that has just been built in the US for nuclear physics experiments relevant for astrophysics, fundamental symmetry, as also societal applications. And as a partner institution, I am actually staying at Oak Ridge National Lab in Tennessee. So as a brief outline of what I would like to talk during these lectures, so I would like just to motivate our interest in the structure of nuclei for astrophysics applications. I will connect a bit with what Ingo has presented during his talk, and also and starting from here, I would also like to introduce the many-body machinery, so the basis from which actually we can build modern many-body methods. It might be actually that few of these things that I listed here can be quite familiar for you. I just wanted, let's say, everybody to be on the same level, let's say. And then I will go into ab-initio many-body methods, and in particular, as a representative example, I will focus on coupled cluster theory, and after this, I will give like an overview of some recent results. So Ingo has already introduced how extreme matter is into neutron stars. From the surface towards the core of a neutron star, we find different density regimes. And in particular, in the core, we reach the saturation density, which is the same density that we have inside the atomic nucleus. And so we have basically here a connection between the macroscopic world of neutron stars and the microscopic world of atomic nuclei. Here, in fact, our equation of state, as Ingo has explained, is dominated by the nuclear interaction. And this is also what Ingo was showing before, so the equation of state of nuclear matter. I just would like to point to your attention the symmetry energy parameters. So J, symmetry energy at saturation density, and L, the slope parameter, which is then related to the pressure of pure neutron matter at saturation density. So if we are at saturation density, in order to understand the behavior of neutron matter, we need to constrain these two parameters. And we can do that by performing nuclear matter calculations, as Ingo has explained, but we can also think about constraining these parameters from quantities that we can actually measure in the lab. And one of them is the neutron skin thickness. So the neutron skin thickness measures the difference between the radius of the neutron distribution and the radius of the proton distribution inside the nucleus. So here I will connect a bit with Chen lectures. So the formation of the neutron skin is related to the asymmetry between protons and neutrons that we have inside the nucleus. So if we are in a situation in which n is equal to z, so symmetric nuclei, we will have that the point proton distribution and the point neutron distribution will actually be pretty similar. And then if we have, let's say, an asymmetric situation in which the number of neutrons is much bigger than the number of protons, we will have that neutrons will be pushed towards the surface of the nucleus, creating a neutron skin. And then if, in extreme cases, we will have that the tail of the wave function will follow an exponential fall-off. And in this case, we will actually have the halo structures that Chen has presented in his lectures. So, and actually, the interesting aspect regarding the neutron skin thickness is the fact that if we consider two different theoretical approaches, so ab-initio calculations and energy density functional calculations employing different nuclear interaction models, we see that in both cases we find a very nice linear correlation between the neutron skin and the slope parameters that we obtain with these different nuclear interactions in the case of ab-initio methods and density functionals in the case of density functional theory calculations. And this gives us an idea. Okay, so if we are able to determine, precisely determine from an experimental point of view the neutron skin, in this case I'm considering lead 208, we are able to use this correlation in order to get a constraint on the slope parameter. And actually, this has been, let's say, the object of a lot of debate, and this is something that I will talk about towards the end of the lectures. But there are also other observables which are important from this point of view. And one of them is actually related to the behavior of nuclei inside electromagnetic fields. So in thermodynamics, if we want to study the equation of state of an ideal gas, what we do is to basically slightly perturb our system and see how macroscopic quantities, as for example the pressure, the volume, and the temperature are changing. And this way we can map out the equation of state. We can think, let's say, in an analogous way here, and we can think of investigating the density dependence of the nuclear matter equation of state, so constraining J and L, looking at situations in which we are slightly perturbing the nucleus from its ground state. And we can actually do that considering the interaction between nuclei and an electromagnetic probe. And in particular, the behavior of the nucleus inside an external electromagnetic field can be modeled, as you see here, so as the absorption of a real photon that produces a transition from the ground state towards a final state. And this final state can be a bound-excited state, or it can be a continuous state, depending on the energy of the photon. And from a theoretical point of view, all the information regarding the possible final states that the nucleus can reach via electromagnetic excitation is actually contained in the nuclear response function that I plotted here. So you see here there are all the different possible excitation energies, so difference in energy between final state and ground state. And here there is basically the transition probability from the ground state towards a certain final state, mu. So how does this response look like? We can focus on a specific class of electromagnetic transition, which is driven by the electric dipole operator. If we are at low energy, actually, this is a pretty good approximation. In fact, what we actually have to calculate when we want to determine the photoabsorption cross-section in nuclei is the interaction matrix element. So this is something like this. So the electromagnetic, so where we have the electromagnetic currents and the potential vector. And we can perform a multiple expansion of this operator, and actually the dominant term in this multiple expansion is given by the electric dipole operator when we are at low energy. And so if we are at low energy, this is actually a pretty good approximation of the photoabsorption cross-section. So in the case of dipole response functions, we have that they look like this. So as a function of the energy of the photon, if the energy of the photon is low, the nucleus will be excited into excited bound states. But then if the energy of the photon overcomes the nucleon separation energy, we will have that actually the nucleus enters the continuum spectrum. And so if we have a large neutron excess, we notice the presence of the emergence of, let's say, a so-called pygmy dipole resonance, a soft dipole mode. And then at higher energies, we have a bigger bump, which is the so-called giant dipole resonance. And these resonances are traditionally associated to internal oscillations of the nucleus, so collective oscillations of protons against neutrons inside the nucleus. We can also, let's say, obtain information regarding how the nucleus behaves in an electromagnetic field by looking at integrals of the response. So if you look at the response function as a distribution, you can calculate energy-weighted moments of this distribution. So it will be something like mn integral in the E, something like this. So you are integrating your response with a weight in energy. And in particular, one quantity, the electric dipole polarizability, is actually correlated to one of these moments, the moments when this n is equal to -1. And it can be calculated from the response function in this way. And what it actually measures from a physics point of view is the tendency of the nucleus to be distorted in the presence of an electromagnetic field. And if we make an analogy to classical mechanics, we can think of the electric dipole polarizability as the analog here of this proportionality constant that connects the induced dipole moment in a charge distribution to an external electromagnetic field. So this is, let's say, the physical meaning of this quantity. And we can actually draw a very similar picture for the electric dipole polarizability as the one that we saw in the case of the neutron skin. So we can take our ab-initio models as well as energy density functional theory models. And if we plot in this case the product between the polarizability and the symmetry energy at saturation density versus the slope parameter, we also see here that there is a nice correlation emerging between these two quantities. And also here, if we have precise experimental measurements of the electric dipole polarizability, I imagine maybe Nakamura-san will say something about it, we are able to constrain the symmetry energy parameters. But actually, so neutron skins, electric dipole polarizabilities are nuclear structure quantities which are relevant for astrophysics applications, but there is actually more. Nuclear structure input is critical in nucleosynthesis simulations. I actually saw that a slide on nucleosynthesis was there in Chen's talk and in Ingo's talk, so I had to have it as well. And so if we consider in particular the origin of elements beyond iron, so the ones that cannot be formed by fusion reactions inside stars, we will have that actually the path towards heavier elements is basically given by a competition between neutron capture rates, which allow us to move from towards like larger numbers of neutrons, and beta decay rates that in itself allow us to move instead towards larger number of protons. And so here there is a competition between these two quantities. So it's important to know half-lives, it's important to know beta decay rates, it's important to know neutron capture rates, and obviously masses, which are at the basis of all of this. But also, if we go even towards like super heavy elements, in this case, we have that processes like fission can become important, because at that point, if nuclei starts to fission, they will, let's say, fragment into lighter nuclei, and so there will be kind of a recycling process in which we go from like heavier nuclei towards lighter nuclei, and then back via the usual R process or S process. And so, let's say, these nuclear structure quantities, these nuclear transition probabilities are extremely important also from a nucleosynthesis perspective. Actually, for example, here I'm quoting like a recent paper where you can see actually the spread around, let's say, the average of isotopic abundance. So here you see the mass number A. And the spread around the average is actually given solely by the uncertainties in nuclear inputs. So in green, in the case of masses, red in the case of neutron capture rates, and blue in the case of beta decay rates. And we actually see that there is a lot that we don't know, for example, especially in the heavier part of this plot. So, and it can actually vary a lot. So instead of being 1 as it should, it could be even 4 times larger. So this is kind of a significant effect that we need to address with more precise nuclear structure calculations. And so we need accurate predictions of all these observables as masses, radii, transition probabilities for nuclei which are as heavy as lead-208 and even beyond that. And so this means that we need to have accurate interactions, first of all, accurate nuclear interactions, and this is something that Ingo has talked about, but we also need to have accurate many-body methods, which are able to solve this equation, scaling up to A, which is around 200. And this is actually a situation in which the complexity of the problem explodes, and actually most of our calculations are running on the most powerful supercomputers that we have available, as for example Frontier, which is actually at Oak Ridge National Lab. Right now, I think the second most powerful supercomputer, because Livermore overcame us a few months ago. And so now the question becomes, okay, how do we can actually model the many-body nuclear wave functions? And in particular, since the complexity of the problem is really high, which kind of approximations are we actually willing to make? And so, like, I will try right now to make kind of an bottom-up approach in which we go towards more and more precise approximations to the many-body problem, and we actually see where we get. So, if we want to model a many-body system, and so a many-body wave function, we can maybe start from one. And so we can start from a single particle wave function that has spatial, spin, and isospin components, and it is the solution of a single nucleon Schrödinger equation. This is something that, like, for now, let's not think about the potential. It can be also simple potential, like the harmonic oscillator potential. It's something that gives us, let's say, a set of eigenstate phi k. How can we combine this? So we can use these single particle states to actually build up a many-body wave function. The many-body space, in this case, will be the product of many single particle Hilbert spaces in which each of the single particle states are living. So we will have that our many-body wave function can be seen as a product of each of the single particle states living in their own Hilbert spaces. And as nuclei are many Fermion systems, we also need to ensure an additional constraint, which is antisymmetry. So to antisymmetrize the wave function, we apply on top of it this operator, which is the antisymmetrizer operator, with which we take into account all the possible permutations that we can make within this many-body, between this many-body product. And for example, if we see that it also depends, it changes the sign on the basis of the number of permutations that we have. So if you have to assign the sign to this permutation, A equal to 4, who is voting for plus and who is voting for minus? I will just give maybe 10 seconds for this. So who is voting for plus? Who is voting for minus? Great. Yes. So the Hamiltonian commutes with the antisymmetrization operator. So this allows us to say, OK, the Hamiltonian and the antisymmetrizer operator, they can have the same eigenvectors. And we call an antisymmetrized product of these single particle states as later determinant. So how this as later determinant looks like, I imagine this is something that you have already seen. You have already seen it? OK, there is someone saying no. So I will just show it. So in the case of A equal to 2, basically what we can do is to take our product here of two single particle states, and we project it on top of the coordinate space. So here we apply our antisymmetrization operator. We will have the same permutation, K1, K2, and then we have the opposite here. So K2, K1. And it changes sign because we did one perturbation. And then we can project it on coordinate space. And this is what we obtain. So here we have, OK, particle 1 in state K1, particle 2 in state K2. And then we have also the opposite. So particle 1 in state K2 and vice versa. And actually, you can recognize in this the determinant of this matrix. So basically, we can rewrite this antisymmetrized many-body product as the determinant of a matrix. Question: how are the antisymmetry requirements for many-body wave functions and the Pauli principle connected? I will give you 1 minute to think about it, talk with your neighbor, and then we can see what is the answer. If you don't like your neighbor, you can also move. Yeah. So somebody who've thought about it can say the answer? Yeah. Exactly. So here we will have that basically K1 is equal to K2, and so and its later determinant is basically 0. Okay. And so in general, we saw the case of A equal to 2. If we consider A equal to, like, we consider in general an A-body system, this will be in general the determinant of an A-body matrix. So, what can, yes?
So in practice, do you put the spin space, isospin space, and coordinate space all together at the same time? Or you try to separate them?
So they're kind of separate because they act on different spaces. So then it depends also on your interaction. So there will be parts of your interaction on which only the spin part is acting or the isospin part is acting, and then parts of the interaction which are just important from the spatial point of view. So in the end, you will have like big integrals in which you basically group your the different components of your wave function. Okay, so let's go to the easiest, somehow, approximation possible, which is the one of an independent particle model. So independent particle model means that we have a many-body system in which particles do not interact with each other. And so in this case, we can actually write our A-body Hamiltonian as a sum over single particle Hamiltonians, and here we will actually have only one index because there is nothing that connects particle I with particle J. I think you have already encountered somewhere some examples of independent particle models. So is somebody willing to share? Yes, the free Fermi gas. This is exactly one of the examples that, for example, Ingo was talking about. The simplest one is just free single particle Hamiltonian. And then we can also have something a bit more complicated. So we add a potential which is only felt by one particle, by particle I. This can be, for example, an external potential. So if we think about atoms, we will have that the Coulomb interaction between the nucleus and the electron is actually a VI interaction. It's an external field. But it can also be something different. We can actually think of this VI as a sort of an average potential, a so-called mean field, which is given by the ith particle, which is given to the ith particle by the presence of all the other particles that we have in our system. And so this is the so-called mean field approximation. So if we are in nuclei, we approximate the interaction of a nucleon with all the other particles by a sort of average potential. So each of the nucleus will feel kind of a mean field, which is actually given by the presence of all the other particles. So here is our Hamiltonian, and so the solution of the mean field Hamiltonian in this case, it's a sum of single particle wave functions, and so it will be obtained by solving the single particle Hamiltonian. And so how does one can write the ground state wave function and energy of the mean field Hamiltonian, starting from single particle states and energies. So we have this linear form. I just give, I don't know, a few seconds to think about it. Or to discuss with your neighbor, if you like them. Yes? So first, the wave function. Yes. So we have single particle states. We build a Slater determinant out of that. And for the energy, you were saying? Thank you. Who is offering something different? It's kind of correct. There is just a subtlety. So the subtlety is the fact that we have to be careful about degeneracy. So it's actually the sum of the single particle energies, but you can have degeneracy in your single particle states. So you have to just take into account that. OK, so how far can we actually go with an independent particle model? So there is actually experimental evidence of shell structure in nuclei. This is something that has been seen like a very long time ago, and also right now is actually like one of the overarching aims, I would say, of ab-initio nuclear physics is actually to get the shell model from first principles. And so one of the experimental evidences of shell structure, for example, is in the binding energies per nucleon. So if we take the experimental binding energy per nucleon for various systems, and then we subtract the phenomenological prediction given by the von Weizsäcker formula, we actually see that as a function here of, this would be the number of particles, but OK, as a function of the number of particles, we will have that this formula is not really precise in certain points, which are defining the so-called magic numbers, so which are 2, 8, 20, 28, 50, 82, 126. And this, let's say, behavior, which has similarities, let's say, with what happens, for example, in atomic physics, is suggesting us that also nuclei have a shell structure. And so basically, we can we can model our wave function, but by putting nucleons inside the shells of well-defined energies. And if we, for example, assume a single particle potential, which is given by attractive central potential and spin orbit force, we are actually able to explain the emergence of these magic numbers. And this is actually what you see here. This was work done in the 60s by Marie Goeppert-Meyer and Hans Jensen, and they actually got a Nobel Prize for it. And so here we have kind of a set of single particle states. We could think about, OK, we start filling them on the basis of the nucleus we are interested in. And then we can calculate the wave function. But actually, like, with this potential, we are not able to actually get a very accurate solution. But still, let's say, just assuming an independent particle model, we are able to get a lot of physics insight regarding the behavior, regarding the structure of nuclei. So how can we get to a better set of single particle states? this is actually something that we can get with the Hartree-Fock approximation. So the idea is that we can start from like the initial harmonic oscillator orbitals, so what I showed you before, and we can minimize the energy, so we can minimize this expectation value in the space of Slater determinants. So what we are doing is basically to find the optimal Slater determinant, the best Slater determinant describing our system. And this actually allows us to find this optimal Slater determinant and also like an optimal single particle basis, the Hartree-Fock basis, which can then serve as an actual good starting point for more precise calculations. I won't delve much into the details here, but if you're interested, I just leave a reference when you can go deeper into the Hartree-Fock approximation. So what happens if we take, let's say, chiral effective field theory interactions and we plug them here? So is the Hartree-Fock wave function good enough to describe nuclei? So here you see results for the ground state energy for calcium-40, 48, and lead-208 from the Hartree-Fock, from like an Hartree-Fock, for the Hartree-Fock method, in comparison to experimental data that come from the atomic mass evaluation of 2020. And actually, okay, you can see that we are kind of off here, right? We're not exactly getting to experiments. There is quite a big chunk of the ground state energy, which is given by correlations on top of our mean field. So this CMAC that I put here in front of the energy is just because the value can slightly vary on the basis of the nuclear interaction model that you choose. Let's say we can have maybe 10% variation, but more or less this is what you get. And it's definitely not enough to explain this discrepancy. So we need something more. And this something more is ab-initio nuclear theory. So the idea of ab-initio nuclear theory is that we would like to choose the degrees of freedom that allow us to maximize our predictive power and at the same time also obtain the finite scale, the finite resolution scale possible. So if we, for example, would like to start from quarks and gluons, that would be actually the fundamental degree of freedom. Those would actually be the fundamental degrees of freedom. However, in that case, we can probably just get to the deuteron. So not very high in the nuclear chart. And so for this reason, our building blocks are protons and neutrons. And then we solve the quantum many-body problem with controlled approximations. So we need to, let's say, in order to do this, we need to model the interaction among nucleons, and we will do this via chiral effective field theory, and this is something you've heard in Ingo's lectures, and suitable many-body solvers. And this is, let's say, the part that I will focus on. So just before going on, are there questions? No, very good. Actually, ab-initio methods have known exponential progress in the last 10, 20 years, I would say. And this is due, let's say, to two main reasons. Obviously, there have been advances in high-performance computing that just brute force allow us to run bigger calculations. But at the same time, people also started working on many-body methods whose computational cost is scaling polynomially with mass number. And actually, this is something you can see here. So you have different colors on on the basis of the nucleus that was first calculated with ab-initio method in the last 15 years, more or less. And you can actually see that most of the nuclei have been calculated very recently. All the blue shades basically date up to 2014. So there has been like a huge progress. And here, like, there are several many-body methods on the market. Some of them were mentioned also by Ingo. And in my case in particular, I will focus on coupled cluster theory. So in order to do this, though, we have to do a little bit of a digression, let's say, and look at in a different way to what I presented before regarding anti-symmetrized wave function. We need to introduce the so-called second quantization formalism. So the idea is that we want a more convenient framework to actually express the states of a many-body system. So we will start still from a single particle basis, but instead of, let's say, labeling it in this way, we can actually look at the number of particles which are in a certain orbitals. So we will have that this corresponds to this Ni, which is the so-called occupation number, and we can create a new basis of vectors, which is like labeled by these occupation numbers, instead of looking, let's say, at the single particle wave functions. And in this case, we have that these states are actually living in a slightly different space, which is the Fock space. And this Fock space is defined as a sum of Hilbert spaces. So we will have that in the first term, this H0, we will have just one state, which is the physical vacuum. No particles exist here. All Ni are vanishing. Then we will have H1, and here we will have like one occupation number. Then we will have two particle states, three particle states, etc. So in this formalism, it's useful to introduce creation and annihilation operators with respect to the vacuum. So we will have that this operator will create a particle, the A dagger will create a particle in a state phi I, and this operator instead will annihilate a particle in state phi I. And every state belonging to the Fock space can be actually computing applying creation operators on the vacuum. So if we have this state here, which will have a certain occupation number N1 in state 1, and 2 in state N2, etc., this can be created by applying N1 times I dagger, A2, N2 times A dagger 2, etc., on the vacuum. So it's a different way of actually expressing the concept of many-body wave function that we see before. So nuclear many-fermion systems, so we need the wave function to be antisymmetric. Before, we were writing it as a Slater determinant in this way. So in second quantization, we can actually just write it as action of creation operators on top of the vacuum. So we have anti-commutation relations here between creation and annihilation operators. And just like to give an idea of how this machinery is looking at, so who hasn't seen this before? There, you have seen it? Okay, very good. So you know that actually here only the anti-commutators between the A dagger and A are actually different from 0. So we are interested in our nuclear Hamiltonian here, where the nuclear interaction is given by Carrel EFT. We will have in general one body, so the kinetic energy, two body and three body terms. And so we can focus on the one body term, which is the kinetic energy. And so in first quantization, we just write it like this. You can also write it in a coordinate space, like as gradient. And in second quantization, instead, we have that the sum has a different meaning. So here we are summing over the particles of the system, and instead here we are summing over the single particle states. So it's a, let's say, a different formalism, let's say, to express also our operators. And so in general, we can do the same thing also for two-body operators and three-body operators. Actually, there is a subtlety here, because as I stressed a lot before, we need to work with anti-symmetrized states. And so we actually need also, like, the two body states that we have here and three body states that we have here to actually respect these anti-symmetry requirements. So, and we can actually, let's say, derive the form of an anti-symmetrized two-body state. Is it something you have already seen? Yes, very good. So instead, let's say, of writing it in this way, where we have, for example, this matrix element, which is PQVRS, we can write it in this way, where this notation is simply, so we have PQRS, which will be and so we have, and we can do the same also for the three-body operator. Okay, so here now we need to introduce two concepts, which are the normal product between operators and the concept of contraction. So if we consider like a normal product of operators, so we have a string of operators, A, B, C, Z. This can be annihilation and creation operators. And this, let's say, and the normal product actually consists in reordering these operators in such a way that annihilation operators will lie on the right with respect to the creation operators. And we will take into account a phase in order to do, let's say, all the perturbations. So why do we bother about operators in normal ordered form, let's say? You need some time to think about it, or you already know the answer? Why? Exactly, exactly. So we care about it because string of operators in normal ordered form gives 0 when applied to the vacuum. And so to calculate normal products, one permutes A, DAGA, A operators, adding a minus sign for each permutation. So if, for example, I have this simple operator, I will have to permute 2 times in order to arrive at the beginning in such a way that we have all on the left. And so I will have just sign 1, and this is the result. Contraction. So the contraction between 2 operators is defined in this way. So we will have that the contraction between A and B is equal to product between A and B minus the normal ordered product. And so we can consider all the possible contractions between 2 creation and annihilation operators. And so which one is non-zero? You indicated it, so you have to say it. This one in particular. So this one is already normal ordered form. And this one instead, as you were saying, is actually non-zero. So the other ones, as you see here, they are 0 because they are already in normal ordered form. So there will be just one combination for which the contraction is different from 0. Okay, so Wick's theorem. So Wick's theorem is actually putting together both these two concepts, so like normal ordered products and contractions. And so if we have a string of creation and annihilation operators, we can actually write them as the normal ordered product plus all the possible normal products with contractions. So we will have that we have to consider all single contractions, all double contractions, and then we will have, let's say, a fully contracted term. And in particular, obviously, as also one of you was pointing out, so only fully contracted terms will survive when we act on the vacuum. So if I have this operator, how does it actually looks like when we apply Wick theorem? So So we have something like this. So we will have just the normal ordered product. Then we will have to do single contractions. So the possible single contractions, we have to take into account that only one of the combinations in terms of contraction is different from 0. So we will have that only this one is actually giving a contribution. So we can contract here, for example, and we can also contract here. So we will have these two contributions. And then we can also take into account the contribution that comes from contracting here. And then we will have a last contribution in which actually we can contract both of these. And there will be only, among all these contributions, there will actually be only one that actually gives a contribution when we act on it with the vacuum. And so it will be this one, which is fully contracted. Because in this case, we have that AQ is equal to delta PQ. And this one will be delta RS. And so in this case, we have that actually this is the only one where we don't have a normal ordered product when we actually then calculate sandwiches with the vacuum. OK. So then in the slides, you will actually find the full expression. OK. For practical nuclear physics calculations, is actually more interesting to start from a different vacuum with respect to the physical vacuum. So instead of starting from the physical vacuum, it is more efficient to define a vacuum given by this, which is in second order quantization form as later determinant, where we have that I, J, and K are occupied all states in what we will call our reference, and A, B, C instead are unoccupied particle states instead above our Fermi reference. And so this will be, let's say, our reference, but we can also, let's say, promote particles from below to above the Fermi sea. And so in this way, we can build excited states of our later determinant. And obviously, like in this case, we can and in this case, so we can actually build a basis, if we want, of different later determinants and their excited states. we actually need to redefine creation and annihilation operators with respect to this new reference. So we will have that. Let's say these two operators are actually both creation operators, so pseudo-creation operators. We will have that this will create particles above the reference, and this will create holes in the reference. So if we have our reference like this, and let's say here are our, so this is the figure that I had. These are our hole states. These are our particle states. If we act there with an operator which looks like this, we will actually get to excited states of this. So we will create a hole in our reference and get a particle, for example, here in state A. And then the contrary can be done by using these pseudo-annihilation operators. So in that case, we can eliminate a hole in the reference, and then we can also, with this, eliminate particles above the reference. Obviously, we also have to redefine our normal ordering with respect to the Fermi vacuum. In fact, we have that, in this case, we'll have that a normal order product will be defined by putting all pseudo-creation operator at the left of pseudo-annihilation operators. And then we will have also that the only non-zero contractions in this case will be slightly different. So actually, they come exactly from what we saw before. So AP AQ, this is equal to, APQ, this is PQ, okay. And so we have to basically consider pseudo-annihilation operators and pseudo-creation operators. And so if we think about this in terms of, this is an annihilation operator, so we consider the combinations in which we have an annihilation operator and a pseudo-creation operator. These are actually the ones that we can obtain. Okay, so we actually have now to normal ordered our Hamiltonian in order that when we then calculate expectation values on our non-trivial vacuum, we can get simpler expressions. And so let's start, for example, from the one-body term, which is the simplest one. Is this one? Yes. Okay. So our kinetic energy in normal ordered form is what I showed you before. So the expectation value of F, AP daga AQ. And then now we apply Wick's theorem. So we will have that this will be PFQ, and this is the normal ordered product, AP daga AQ, plus, again, sum over PQ, PFQ, AP daga AQ, contracted. And then the only contraction that actually here is giving a contribution is the one where we have that we are considering indices which are of the reference, so of our holes. So this one. And so we get PQ, okay. Plus, now we have delta ij, so we will have to sum over EFI Yes. So this is, let's say, this part here will be the actual expectation value of our operator on the vacuum, and that's what we get. We can actually do the same also for, in a, let's say, with a more boring way, we can do the same also for the other operators. You can actually get excited by doing this in the exercises for V. So here is how it looks like, the result for V and for W. So what we notice is that there are 0 body terms, which are actually the expectation value of our Hamiltonian on the vacuum. These are the only ones that survive when we actually consider a sandwich with our reference state. Then we have 1 body term, 2 body terms, and 3 body terms. Actually, one thing that is usually done in ab-initio calculations is to perform the so-called normal ordered 2-body approximation. So basically, what we do is to ignore this term here when we actually add like a nuclear interaction that has a 3-body force in our machinery, because as you can see, like part of this 3-body force is actually somehow included in our framework by one body and 2-body terms. And this is actually very convenient because the storing of 3-body matrix elements is a challenge for ab-initio calculations, as it can easily get above 100 gigabytes, which is like kind of a relevant portion of the space that we have on nodes of typical workstations. Okay, so we can group, let's say, 0, 1, 2, and 3 body terms in our Hamiltonian. We will get H0, which is the contribution that comes from the expectation value on the vacuum. And then we have the normal ordered 1-body, 2-body, and 3-body part. And so in this case, what we see is that we get part of the energy actually from our expectation value of the Hamiltonian on the vacuum, so from our H0. This will be the energy that we get from an Hartree-Fock calculation. And then we get the correlation energy, so the difference between our exact ground state energy minus the Hartree-Fock ground state energy, the correlation and the so-called correlation energies. We can get it from coupled cluster theory. Okay, so before going into this, are there questions? No. Good. How far am I doing in time? 15 minutes, okay. So actually, coupled cluster theory is a pretty interesting story because it was formally introduced at the beginning in around like in the 70s in nuclear physics by Koester and Kummel. There are here some people from Mainz, so you should know that actually Kummel was working in Mainz at the time. So actually, like there is some pride of getting a PhD in coupled cluster theory from Mainz. And but actually, at that time, computers were not powerful enough to actually make coupled cluster theory applicable in nuclear physics. And so it actually became very popular starting from the late 60s in quantum chemistry. And this is something that and actually, like most of the developments of coupled cluster theory have been done in quantum chemistry. And then, let's say, towards the 90s, in that case, obviously, there is also, let's say, a simpler interaction to deal with. And then towards, let's say, the end of the 90s, okay, computer starts to be a bit better. So there was actually a renaissance of coupled cluster theory, in particular, like some groups like Bishop's group, and also Heisenberg and Mihaila, and then the group that I'm part of in Oak Ridge. They are all working in coupled cluster theory for nuclear physics. So what is the actual basis of coupled cluster theory? So the idea is that, okay, we start from the Schrödinger equation for the ground state of a nucleus written in the normal ordered form. So our target is the correlation energy. And we solve it relying on the so-called exponential ansatz. So here, this exponential ansatz is actually connecting our ground state wave function to the reference state, to our Hartree-Fock reference state. And so we can look at it as a way of adding correlations on top of our mean field, on top of our mean field solution. The correlations in particular are determined by the shape of this exponentiated operator T that we have here. This is the so-called cluster operator, and we can write it in this way. So we will have that it is a sum of one body, two body, three body terms up to A body terms. And these terms looks like this. So they are basically particle Hall excitations on top of the reference. It's what I was describing here. So if, for example, we just keep in this expansion T1, we will have all the possible configurations that we can actually reach by creating a hole in the reference and putting a particle in our particle states. The same we can do also at the two-particle two-hole level, three-particle three-hole level, etc. If we were actually able to get up to a particle A-hole level, well, that will be an exact calculations. But actually, most of the times, we are limited, let's say, in this range here, unless we maybe consider very light system like the deuteron or tritium. Okay, so let's insert the exponential ansatz in the Schrödinger equation, and this will give us also like kind of a more productive view of what this similarity transformation does. So we have our psi 0, e to the t, phi 0. We want to insert it in our Schrödinger equation. So we'll have hn e to the t, phi 0 in this case. So we went to the reference. We can multiply this equation from the left by e to the minus t, and here e to the minus t. And here we can define this object here as the similarity transformed Hamiltonian. And then here we will have that simply these two exponentials will go away. And so we will have delta E0, phi 0. So basically, we can also think about coupled cluster theory as finding that similarity transformation that is able to, for which the reference state is actually the ground state, and the correlation energy is the ground state energy. So it's a different way of just looking at this problem. So Hn, if we use, let's say, the definition that I gave of cluster operator, you can actually show that the similarity transformed Hamiltonian is non-Hermitian. Why? I would like you to think about it maybe for a minute, or discuss with your neighbors. Eh? It's this one. Yes. So the simplest way maybe to see it if we just consider like the first few terms. So if we have, I don't know, just the one body part, it's useful to have it here maybe. Does somebody have any idea? Okay, so actually it turns out that Hn, so the similarity transformed Hamiltonian, is non-Hermitian for whatever truncation you actually use. And we can look at it in this way. So let's, for example, calculate just the adjoint of our similarity transformation. So we have this. Want to calculate the adjoint. So when we calculate the adjoint of a product of operator, we have to shift them. So we will have e to the t dagger. My t look like too much like a dagger. Ooh. Okay. Ooh. I don't know what this is. Okay. Yeah, it didn't like it. Okay. So maybe I had this one in my hand and it was doing weird stuff. Okay, so h e to the minus t dagger. So, and if we actually dagger everything, we will have t dagger here, h e to the minus t dagger. And this is actually different with respect to e to the minus t h e to the t. And you can see that because this is actually an excitation operator. So like t is an excitation operator. As we saw, it's like just a sum of these strings, one particle, one hole, two particle, two holes, etc. And in general, if we consider e to the t, this will be 1 plus t squared, etc. Excitation operator. The same also on this side, there will be just a different sign. So our exponential here will be just 1 minus t plus t squared minus t to the third, okay, with some factors, but that's the idea. So we have that on both sides, we have something that it's an excitation operator. While when we calculate the adjoint of an operator like this, we actually obtain, so for example, just for T1 is sum over IA, IA, I dagger AI. We will have something like T1 dagger, which is sum over IA, TIA, AI dagger AA. So this is actually a de-excitation operator. So it's a completely different object also from a physics point of view. It creates a different excitation in our Slater determinant. And so that's why our similarity transformation is actually non-Hermitian. Okay. So as I was saying before, it's a very challenging, yes? Exactly, exactly. So like this is not a problem at the level of the ground state energy, but when we calculate, and this is something that I will show at some point, when we calculate expectation value of observables, the actual consequence of having a similarity transformed Hamiltonian, which is not Hermitian, is that we have to be careful about the fact that our brass state is different from the right state. And so there will be like a different coupled cluster expansion when we calculate the left part, let's say, of our problem. So, okay, we have that. Using the full T expansion here is too expensive. It needs to be truncated at some point. And so there are different possible truncations, obviously. Like the first one, CCSD, is actually the one that it's mostly used. And it's the cheapest, I would say. And it scales here, as you can see, as number of occupied states in the reference squared multiplied by nu to the fourth. Nu is the number of unoccupied states in the reference. So if we have typical numbers for these a number of unoccupied states, for example, if we want to have a converged calculation, usually we will consider a model space which has like around 200 single particle states in total. So we will have around 200 here to the fourth. So pretty, yeah. This is the cheapest, but already pretty important. Here we go even worse. So this is a CCSDT. We add also 3-particle free Hall excitations in our reference. And so in this case, okay, like here, if we will have that usually the term that contributes the most is actually this n to the u, but we could write this as n to the 8, and so here it will be 200 n to the 8, a lot. And also here, if we go even further for particle for all excitations, here it will be n to the 10, etc. Actually, for example, like in chemistry, they're able to get even to CCSDTQP, so even to the 5th term in our expansion. They have, let's say, a simpler Hamiltonian to deal with. In the case of coupled cluster theory, we are actually limited to approximations of the CCSDT framework, for which we won't have maybe the total cost of a coupled cluster, a full coupled cluster with triples, so which is n to the 8, but we will have something maybe more manageable around n to the 7, more manageable. But you understand how complex these calculations can be. And for example, this is another aspect that I will probably show in the results or later in the lectures, is the fact that, for example, these 4-particle for holes effects can be quite important in some cases in nuclear physics. As for example, if we think about clustering, if we want to have a cluster in our system, we actually this is something that Chen was talking about. We have halonuclei. We typically have clusters of inside halonuclei. And so to get them fully, we would need to have 4-particle for Hall excitations. And so this is, let's say, an inherent limitation, limitation of the method. OK. So let us focus on the simplest case, so the coupled cluster singles and doubles case. I don't know how I'm beyond. No, you should stop me. Yeah. How much you have? I can finish later. It's no problem. Yes. Yeah. No, like. Yeah. No, like here, like you should stop me because. Yeah.
Maybe this part we can leave.
Yeah, for the next one. Yeah.
At least one or two questions.
Yeah.
And then in
Okay.
the afternoon you are going to discuss. Maybe
Yes.
you can at least put
Yeah.
something.
Okay.
So some questions to Francesca.
Yes.
Can you use SU for symmetry and just assume that they form into alpha and just limit your model scale?
That's something we are actually thinking about for this application. I think like there were some also some work like done by lattice effective field theory in this direction. We are thinking about a lattice version of coupled cluster that maybe could, let's say, have some advantages here also for this. Yes. Yes. Mm-hmm. Okay.
What does that mean physically, that there is a correlation?
So the correlation is something that comes from the theory. And it's somehow a way that you can use to test your nuclear matter calculations, for example. Because you want to, let's say, make a connection between your theoretical calculations, because in the end, the symmetry energy parameters are something that you calculate, right? They are part of your method. You determine them from a theoretical point of view. You want to have kind of a connection with experiment that allow you to test your prediction for these parameters at a certain density. In this case, it's saturation density.
Then maybe like in a simple case, like let's say a large polarizability.
Okay.
What like a large probability, because that's a linear correlation.
Yes, would mean
like
a large polarizability would mean like a larger value for L, which would mean like a stiffer equation of state. It's the same problem that you get actually for the neutron skin. Like the P-Rex experiment is actually predicting like a larger value for the slope parameter because it's a larger neutron skin.
Yeah.
The polarizability constraints instead are going in the opposite direction.
But like, do you have like a easy physical intuition? Like, what does that mean? That, you know, like...
Okay, like you can think of the fact that both observables, like the neutron skin and the polarizability, are sensitive to the asymmetry between protons and neutrons. So like you have basically that protons and neutrons behave differently when you are in an electromagnetic field, for example. And so this determines, let's say, the sensitivity of these observables to parameters that actually measures the contribution to the energy per nucleon given by the asymmetry between protons and neutrons.
So the last question, we will have the discussion with Francesca.
Do you have an idea of how much it impacts in the theory to add a term in the expansion of T? I mean, how much increasing, because the cost of adding another term in the expansion is huge. So how much it will affect the result?
So this is like uncertainty coming from the truncation of the many-body method is a systematic uncertainty. And the way for us to estimate that for now is to look at what we get from different truncations. For some observables in particular, we have a very clear idea of how much we get passing, for example, from coupled cluster singles and doubles to like the best triples approximation that we have. And in that case, for example, for the ground state energy, I can tell you, okay, 10% of the correlation energy is actually given by triples. For other observables, we just have trends. For example, for the radius, actually, the effect is very small because already like the mean field solution for the radius is not so bad. So in that case, the effect of adding triples is really, really small. But for example, in the case of the polarizability, we see that the typical trend for going from CCSD to CCSDT is just to bring it down. At least in medium mass nuclei.
Francesca, we have to thank you
Yeah.
now.
Thank you.
Today we are late. I think we can start at 2 to have time to lunch instead of